Thank you, Lee. After that introduction, I don't know if I can speak. But thank you so much for being here with us and for your wonderful comments today. What I thought I would do for you today is really give you an overview of where we are with this field of making tissues and organs off the shelf. This is actually a painting that hangs at the Countway Library at Harvard Medical School, and it shows the very first time that an organ was ever transplanted. In the back room, you see Harwell Harrison, the chief of urology, retrieving the organ, while in the front you see Joe Murray actually getting the patient ready to receive the organ. The very first organ to have ever been transplanted was a kidney, and that was back in 1954. So many challenges that were overcome by that one single event, but we're still dealing with a lot of major issues with donor shortage. We have a major problem with organs, not having enough organs to go around. In fact, the statistics are fairly serious. About every 30 seconds, a patient dies from diseases that could be treated with tissue replacement. So that is where this field comes in, this field that we call regenerative medicine, which really allows us to create tissues and organs using the patient's own cells. And we can use either cells alone or scaffolds, which are just materials like a piece of your blouse or your shirt, or cells and scaffolds together. And we, for example, can zoom in for you and show you some of these technologies. Like we can use scaffolds alone. And this is actually a machine that we use in this next slide that shows how we make these scaffolds. This is like a cotton candy machine that you would see at your local fair. And instead of making cotton candy, it's actually creating these fibers that can disintegrate once inside your body. And we can create these tubularized structures that we can then use as a scaffold to regenerate tissues and organs. And we can use some of these scaffolds that you see here, and we can actually make them go into replace tissues and organs. This is actually an organ that you see here from a patient. This is an injured organ. You can clearly see the defect on the top portion of the organ. But the bottom portion of this tubular organ is still okay. So what we ended up doing is we replaced the top portion with this material that we made in the laboratory, and we used that as a scaffold, if you will, as a bridge, allowing the patient's own cells to regenerate over that bridge and create a new organ. And you can see on the bottom right the fully regenerated organ that was implanted in a patient, just using the scaffold alone without the cells and allowing your own body's natural ability to regenerate to take over. But interestingly, that it only works for small segments of tissue. For larger segments, you absolutely need the cells. The scaffolds alone will not work. You need the scaffolds and the cells. Now we can also use cells alone. For example, we can now take a very small piece of tissue from a patient, less than half the size of a postage stamp. We can take that piece of skin in this example I'm going to give you. A patient who has a burn, we take a very small piece of normal skin from that patient, less than half the size of a postage stamp. We're able to expand and dissect these cells right there in the operating room, and then implant them with a spray machine onto the patient in the area of the burn. And this is a technology that was developed initially in Australia, and we now have about 10 centers in the U.S. that are experiencing these technology with patients, with Wake Forest leading this trial. We can then use cells and scaffolds together. So what we've done here is these are for patients who have larger defects, and the scaffold alone will not do. As I mentioned, if the defect's too large, you need both the scaffolds and the cells. Again, these scaffolds being just like a piece of material that you would see in your own clothing. But these materials are designed to degrade once inside the body. So the concept here is that you do need a tissue to be replaced. You go to the patient, you take a very small piece of tissue, less than half the size of a postage stamp, you expand the cells outside the body, and then you take this piece of scaffold that you're going to create, and you place those cells on the scaffold. Very much like baking a layer cake, if you will. You're just placing those cells on that material layer by layer. And so this is actually a piece of muscle that we created. And these are muscle strips. So we took a piece of muscle from the patient, we expanded those cells, place those cells on these scaffolds, and we are now exercising the muscle strips that you see here. And then this muscle will now acquire the properties needed to go back in your body. Now, in addition to some of these technologies, we're also using cells and scaffolds for larger defects. This is actually a patient who presented with a motor vehicle accident, had a traumatic injury to their organ, and you can clearly see the defect. You can clearly see that there's a defect present there that cannot be replaced just with a scaffold alone. So we went, brought the patient in, took a very small piece of tissue from their organ. We grew and expanded the cells outside the body. We then placed, it's made up of two different cell types, this particular organ. So we placed one cell layer on the outside. We placed another cell layer on the inside, again, very much like baking a layer cake. We then placed that in a bioreactor, which has the same conditions as a human body. It's like an oven-like device. We let it cook there, if you will, for a few weeks. We then are able to take that tubularized structure that's now fully seated with the cells, and we're able to implant that back into the patient. And now you see the patient prior to surgery on the left, and the patient's x-ray on the right with their fully regenerated organ. And we now have patients who are more than 7 years out with this experience that we publish in this medical journal. Now, we've also tried to achieve the same type of strategy using other organs. This is actually a blood vessel. Same concept here. What we do is we take muscle cells, place them on the outside. We take blood vessel cells that line the inside of the vessel, place them on the inside. We use these bioreactors. These bioreactors actually exercise these blood vessels prior to implantation. And on the far right, you see this artery. This is the carotid artery that goes from the neck to the brain that was replaced experimentally using these techniques. Now, we've talked about structures. This is a little bit more complex. This is a heart valve structure. Same strategy here. We're using these bioreactors, again, to mature the tissue in the laboratory before they get implanted. Now, we have not implanted these in patients yet, but you can see how we're creating these structures. These are the heart valve leaflets, opening and closing, again, conditioning the tissue before we implant it into the patient. Now, we've talked about flat structures such as skin, they're definitely the simplest to create because they're flat, mostly one cell type. We've spoken about tubular structures like blood vessels. They have two different cell types. They're tubular, a little bit more complex. But hollow non-tubular organs are at the third level of complexity. They're more complex because these organs are they're architecturally more complex. The cells are more complex. The functionality of the organs are more complex. And the bladder is one such organ. Same strategy here. We take a very small piece of tissue from the bladder. We expand the cells outside the body. We bring the patient in 6 to 8 weeks prior to their scheduled surgeries. We expand the cells outside the body, create this three-dimensional structure. We coat the outside with the muscle cells, the inside with these lining cells. We place this structure in a bioreactor, this oven-like device, and 4 to 6 weeks later, we're able to place it back into the patient. That's what you are seeing here. And the next slide, you're going to see the three-dimensional bladder that has been created experimentally, and we've been able to implant these in patients. We're over 10 years out now with this experience in patients using their own tissues. We actually implanted the first one about 13 years ago. In the next slide, we will see another strategy to create organs, and this is actually a strategy to create organs using printers. This is an inkjet printer cartridge, but instead of using ink, we're using cells. And this is an adapted desktop inkjet printer, but instead of, and you're going to see the cartridge go back and forth, and the cartridge is actually printing the cells with a biogel together. This is your typical desktop inkjet printer. It takes about 40 minutes to print. About 4 to 6 hours later, you start to see the cells beating, the heart cells beating for this three-dimensional small miniature heart that we're creating. Now, we're also looking at more complex printers. That was our first rendition of over a decade ago, over 10 years ago. We are now using much more complicated printers. Let's say we want to create a kidney. So what we do is we go to the patient, we get an x-ray of the patient, and once we get an x-ray, we know what the kidneys are going to look like. We then do three-dimensional computerized imaging analysis using just the patient's own x-ray. And three-dimensionally, we can see what the organs look like. Layer by layer, we can go down to the actual organs. We then can take the information from these organs, then transfer that information to a printing system, and then through the printing system, what we see is basically the information going into the printer, and then the printer actually acquiring this information and creating this structure one layer at a time. Again, using the same type of strategy that I showed you before, but using much more sophisticated printers. So basically, what we see here is really miniature kidneys that we can engineer now. We have been able to engineer these miniature kidneys that we're able to implant into cows and steer, and they're able to secrete urine, as you see here. And so the strategy for us now is to create these larger structures that we can actually implant into patients in the future. So basically, to summarize then, what I've tried to do for you today is really give you an overview of where we are in this field that we call regenerative medicine. And we're working at the Wake Forest Institute for Regenerative Medicine in about 30 different types of tissues and organs, and about 20% of these are already in patients today. And our challenge for us for the future is to be able to bring more of these tissues, and that's our goal, to keep bringing more tissues to patients in the future. And these technologies really have several types of benefit. First, of course, the most obvious is the benefit to the patient itself. Basically, the Human Health Services has declared this technology really one of the major changes for the field of medicine for the future. So you have the patient benefits. Then you also have the healthcare cost benefit, because these technologies have the potential to not just manage disease, but they also have the potential to cure disease. So instead of having to manage a patient long-term with medicines or therapies like dialysis, you can just treat these patients and then allow them to recover in a faster manner. In addition to healthcare cost benefits, there are economic benefits, because as you know, this is as you can imagine, a large market of about 120 billion by 2015 that can be in fact used by these technologies that we call regenerative medicine, that can be manufactured right here in our state of North Carolina for the benefit of our patients. And finally, there are job creation benefits, because as you know, when you're talking about biotechnology based jobs, for every job in that sector, there's a multiplier effect of about 5.7 jobs for every one job in this area. So also in terms of the healthcare landscape, this has job creation benefits. And there is no better place to do this than our state of North Carolina, where we are poised in this area to really bring these technologies not only to our patients today, but to our wounded warriors and other segments of our population in the future. And by allowing us all to work together, we can accomplish this. And we have major collaborations and work. For example, we're working extensively with NC State in the area of being able to bring these technologies to the veterinary market, to the veterinary patients. And we're working closely with Atala Piedrahita, who you're going to hear from in a few minutes. We're also working with NC State, for example, in the area of manufacturing. We linked up with Paul Cohen and his group. He heads the EdFITS, the School of Industrial Engineering, to look at how we can actually scale up these technologies and really go after this manufacturing sector in a major way. So having these collaborations within the state is a great thing that will allow us to advance these technologies for the future. And finally, I leave you with one brief video clip. This is actually a clip that is from a patient treated with one of these technologies.
I could barely get out of bed. I was missing school. It was just pretty much miserable. I couldn't, go out and play, basketball at recess without feeling like I was going to pass out when I got back inside. I felt so sick. I was facing basically a lifetime of dialysis, and I don't even like to think about what my life would be like if I was on that. So after the surgery, life got a lot better for me. I was able to do more things. I was able to wrestle in high school. I became the captain of the team, and that was great. I was able to be, the normal kid with my friends, and because they use my own cells to, build this bladder, it's going to be with me. I got it for life, so I'm all set.
That's Lucas Masella, He's now actually now 11 years south of having received his engineered organ. I had the pleasure of seeing him again last year after 10 years of having his implant. We still have many challenges ahead. We have many more organs that we need to target. We still need to define the best patient populations. We still have regulatory challenges, cost challenges to address, manufacturing challenges. So we still have a lot of work to do. But there's one thing clear, and that is that regenerative medicine, the promise of the field, is not about the cells we use or the technologies we choose. We know that these technologies are able to benefit patients, and for us, that's what it's all about, making our patients better. Thank you for your attention. Thanks, Lord.
That's going to be tough. But now you understand why we partner with them. Clearly, it's an amazing work that they do there. So what I'm going to show you today is what we're doing in the veterinary field and how we are partnering not just with Tony's group, but also within the state, within the NCSU, and have formed a fairly large group that brings multiple expertise to try to deal not just with the veterinary field, but also with the manufacturing problems, which are barriers which are pretty substantial. So in a very simple terms, this is more or less what a regenerative medicine product looks like, or project looks like. You have a donor. In this case, I put one of my colleagues, Rick Fish. He doesn't need a new ear, but he probably could use some new hair, but regardless. You take a sample from that particular individual. It could be a human or it could be an animal, and you take a tissue biopsy, whether it's muscle, whether it's cartilage, whether it's heart, some part of the tissue that you want to expand. You isolate those cells, you expand those cells a certain period of time, you harvest those cells. If you're combining those cells with a matrix or with a scaffold, now you have to manufacture that scaffold and have those requirements met. Then the two shall meet, and then you have to put these cells either in a bioreactor, or in this case, this is work from Tony's group, they put it in a mouse, in the back of a mouse. And at the end of the day, that tissue should go back into the humans or into the animal that you took the tissue from. So it's a full circle. But you can see that there's multiple steps. And it's not just about the biology. It's a tremendous amount of engineering involved in that particular process. So I want to tell you a little bit before we start, so there's no misconception about what we're doing. We are strong believers in the One Medicine concept. And the One Medicine concept is a very simple concept that says, anything that you learn in one species can be applied to another one. So we live in the veterinary school, but the animals are patients for us. They are not experimental animals. So the work that I'm going to show you in cats and dogs are not experiments done to hurt the animals. They are clinical trials trying to develop these technologies. For us in the veterinary school, those animals are our patients. They are not experimental animals. So we use clinical trials. We use other species to get to that particular point. So I show you the complexity of this field. There's no way we're going to solve the issues related to manufacturing in this field unless you put the proper team together. And we're extremely fortunate to be in this state because we have all the proper pieces. And not only we have all the proper pieces, but we have very high quality proper pieces. Number one, we've been able to partner with Wake Forest. You just saw the amount of the unbelievable science that they're doing. Clearly a very, very strong partnership. We also have UNC and Duke Medical School. So we have a very strong human medicine community. But we also have a world-class engineering program. We also have a world-class veterinary program that's considered the third in the nation and probably the most modern veterinary hospital in the world. We also have one of the best, if not the best, textile program in the world. And if that wasn't enough, we have BTech located right by us, the Manufacturing Training and Education Center. And so the program that we're building includes from the very inception of the program a manufacturing component. So BTech has helped us design a facility that is going to test the new generation of protocols to produce regenerative medicine products. So from the very beginning, we're considering manufacturing in the design of the projects, which is one of the areas that has been a problem. The biologists like me go and develop these amazing technologies. Then we take to the point of commercialization. We meet with somebody that's going to help us do that, and we realize that there's all kinds of manufacturing issues that we didn't take into account. And we want to take them into account from the very beginning. So the key areas of research for us are these three, we call them the great barriers of regenerative medicine. Number one, we're using cells from the patient, and those cells are going back into that patient. We have to deal with what happens to those cells when they're being cultured. Number two, the mouse is not a useful model for regenerative medicine. You cannot produce a heart that's about this size and expect that that same component is going to behave the same when you build a heart that's the size of ours. So you need to work with an animal that has the proper physiology and the proper size. So you have to have an adequate animal model. And in manufacturing, as I'll show you at the end, this field is huge barriers to manufacturing. There's a tremendous amount of difficulties because of the issue of dealing with living tissue instead of inert material. This is a very simple example of what happens to cells. This is a project that we're doing with the engineering and with Wake Forest on chondrocyte growth. There's 4 different culture conditions. The higher the number on the y-axis, the better the cell it is. So high numbers mean good quality cells. So you can immediately see that the cells behave very, very different depending on which media they are. So the group culture in the lowest SFM, that I won't go into details, that obviously has a very high number. So the culture system, very great influence on the cells. But what's more frustrating is what happens with time. So freshly isolated cells look fantastic. You pass them once and look at what happens to that number. That thing goes to almost 0. So the cells are fluctuating in culture, and we need to understand that fluctuation. We need to control that fluctuation, and if possible, we need to revert that fluctuation. So again, we have to figure out how to grow these cells and expand them without losing the characteristics that we want them for. Animal models, again, like I mentioned before, mice are completely useless for this kind of stuff, right? You can develop a certain amount of information, but at the end of the day, if you want to move to the manufacturing, if you want to move to the clinical trials, if you want to move to the application, you're going to have an animal that resembles a human in some sense, shape, or form. And we're very lucky to have 2 very strong programs at state on that area. In the swine area, we have one of the only programs, there's only 2 academic programs in the United States that can generate very complex genetically engineered pigs for use in biomedical research. State is one of them. The pig is an amazing research for biomedical research. It has been used forever in cardiovascular disease for developing medical devices. So it's an animal that we're very used to working in the biomedical setting. But the dog and the cat, the companion animals, play also a key role. And I'll tell you why that key role is so important. Because here's the deal. When we develop a technology in experimental models, those animals are highly homogeneous. We have a group of rats or a group of pigs that are all the same age, they're all the same sex, they're all the same weight. We're doing the same kind of manipulation on them. Then we test our compound, we test our protocol, and we find the protocol that works the best. But then we move to a human community, and we are all incredibly different, right? Different in age, different in weight, different in racial background, different how we respond to drugs. That heterogeneity, we're going to have to learn how to deal with it. When we develop these protocols, the development of the protocols needs to include a population that is heterogeneous enough so that the protocol that we're developing works in all of them or most of them, not just in a very narrow group. And the natural recurring population for us is the dog. They get most of, if not all of the diseases that we get. They get cancer, they get diabetes, they're obese, they get fractures, they get spinal cord damage, they get kidney failure, they get heart disease, you name it. We have a certain type of disease. There's some dog out there that's going to have a very similar or identical disease, but they are heterogeneous, and we treat them in our hospital. We see about 22,000 patients a year. So they're coming to us for help, and we're seeing that heterogeneity. So what we're doing is we're developing the technology with the help of groups like Tony's, and when we know that technology is safe, and then apply it to the animal community or these animals that we're dealing as patients, and learn how to work with that heterogeneity to slowly improve the system so that when we move it to the human clinics, it's the best system possible. So now let's think from the manufacturing perspective. Now it's the same slide as I showed you before, and here are the barriers. Number 1, that animal that you're starting with, I just told you, it can be different age, different sexes, different breeds, different weights. We have to deal with the variation. We have to take a sample from that animal. Where do we take that sample from? How big is that sample going to be? We're going to isolate those cells. How are we going to isolate those cells? Are we going to use method A, method B, method C? How are we going to expand those cells? I showed you at the beginning how different culture conditions affect the cells. Variability. If you're doing a manufacturing process, variability is a killer. And this thing is chock full of variation all over the place. The same if you're using the scaffolds. Now you have a three-dimensional matrix. That one is a little more easier to deal with because it's an inert material in some cases, although in some other cases it's a biomaterial. You have variability included in there. So at the end of the day, these processes are basically variability in cells, variability in the process, as in the culture system, how you collect those cells. We've seen variability in the technicians, which is huge. One person takes that protocol that's sent by a particular group and gets outstanding results, and another technician that's sitting right by them takes the exact same protocol and gets less than stellar results. So what we're trying to do is, number one, understand that variability, and number two, try to automate as much as possible to take out the human component, to take out the process component, the process variability out of the system, so we can end up with a better process for producing these regenerative medicine products. And I'll just close with this one. Basically, I hope I convey the complexity of what's going to happen when we start developing these organs in a commercial setting and scale up in regenerative in manufacturing principles. And we cannot solve those manufacturing problems unless you put a very complex interdisciplinary team together. And we're very excited because we think we have a good team to start addressing some of those questions. Thank you very much.
Thank you, gentlemen. How wonderful and how interesting. We do not have a lot of time, but we do have some really thought-provoking questions from the audience that we really want to get to you, if you don't mind. So I'll ask them if you can just kind of do a real quick summary. We'll hopefully get to maybe 2 or 3 of them. First, Tony, the work that you're doing, you talked about a patient that had a really bad car accident and had injury to the bladder. We normally think of accidents, and spinal cord injuries are more prevalent. Is regenerative medicine in the area of spinal cord injury?
It is, and so there are many, many areas that are being explored. Spinal cord is actually the toughest because you're really looking at a cord that's made up of literally thousands of nerves going in every direction. But there's definitely work being done in the area, and hopefully that'll yield some results in the future.
Great, thank you. Jorge, we talked about our beloved animals and, of course, our humans. And this technology, since it's so new and leading edge, we have to conclude it's very expensive. What things can be affordable? How do we make it affordable? I just personally can't see it being included in Blue Cross Blue Shield or United Health Care Plan. How are we really going to make this effective to people if it's not affordable?
That's an excellent question, but I think if you understand the manufacturing process really well, then you can simplify the process. Like right now, it's very costly because there's a tremendous amount of labor involved. You have a specialized technician collecting those cells, a specialized technician growing those cells. But if you can automate that process, it might be possible to lower those costs quite a bit. Now, the clinical component is never going to change. You have a patient, you're going to do a surgery in that patient, but it's an alternative. It's not like this is going to solve everything. This is in addition to the existing technologies, and there's diseases that we just don't have adequate technologies. So the choice is, there's something available. If you either get it or you die, is it affordable or not? We will try to make it affordable, but I think the situations that it's just a choice of you need it and you have to have it.
Okay, thank you. And just as a conclusion, I mean, obviously we're talking about science, but I'm a businesswoman. There's a business component about it. You mentioned, Tony, that this particular sector can create 5.6 follow-on jobs. How do we take this to a wider scale? What policies, what things do we need in place to really bring this out throughout our state and our country?
That's a great question. We are so fortunate, of course, to have right here in our state the Institute for Emerging Issues, right?
Right, that's right.
So we are very fortunate, and thank you all for putting this on. And I think that having this type of policy analysis that is always directed at how can we strengthen our position in our state. We did it, we've done it now many times. Governor Hunt did it when he was a pioneer in this area for the field. I think we can continue to do this as we move forward, as long as we put the right policies in place. And of course, that'll include governmental policies, funding areas as well as reimbursement policy for patients.
Thank you so much. Governor Hunt?
Well, aren't we excited about this work that's happening and that it's happening in North Carolina? Thank you all so much. We're so proud of you.